So now to the big picture.
Mm-hmm.
So quantum computers employ the behavior of fundamental particles for computation. It arranges a set of quantum wave functions and arrives at results through the interference pattern. So,
Mm.
yeah, as I said, quantum circuits are like matrix operations, but the way to physically think of it is that it's like an interference of waves that basically it's it can be mathematically represented as different spins on the particle.
Mm.
But yeah, it encodes a lot of information, and the resulting interference pattern, when it's observed, can be used to uh, arrive at like computational results.
Mm.
So yeah, in classical computing, when we had just circuits and switches, the only major concerns were time and space complexity, like how
Mm.
long the algorithm took to complete, because
Mm-hmm.
each step was performed subsequently.
Mm-hmm.
Um, and space was like how much it would store, how much and space is like how much data it could store, or how
Mm.
much it had to keep in memory, because some algorithms depend on like keeping track of previous answers. Um, with quantum computing, we also worry about the probability. So there's like a new type of complexity,
Huh.
even though like as I said, it definitely it definitely helps with like time complexity, because like everything's like it can be super like hyper parallelized,
Right.
and space complexity, it also like gets lots and lots, like exponentially more storage the more
Mm-hmm.
qubits you can maintain.
Mm.
But the thing is that because of like there's like we'll also worry about like the probability of the answer. So like they're fundamentally stochastic in nature. So like they're not like you're not dealing with like definite values, you're dealing with probability distributions.
Mm.
So they can manipulate it so that mathematically they know that they have a certain confidence interval for the answer, but like it would never be 100% certain. Um, some things that like the way quantum computers might be applied might be is that they might be used to arrive at an answer that can be like verified pretty quickly in classical time. For instance, like like NP problems
Mm.
are problems that are like exponentially complicated, but they can be verified pretty quickly.
I thought I thought each uh, all the results reached by quantum computing are equally possible. They are just they are the result of
No,
different.
no, that's not true. So only in like the basic, like the standard qubit state, I think does have zeros and ones with equal probability.
Mm-hmm.
Um, but depending on the type of spin, the probability distribution changes.
Uh, what what changes
The probability distribution
of what?
of the answer, like of zero, like it could be zero, like depending on the spin, it might be
Mm.
more likely to be one or more likely to be zero.
So you're talking about the end result, not each step.
Yeah, the end result, the observed state.
So the each in each step, each state has equal probability.
Not necessarily true either. Like each state is in superposition, and
Uh-huh.
like depending on the type of superposition, like the spin of the particle, there are different probabilities. Like there's a different probability distribution.
Mm.
So yeah, they like mathematically they yeah, I mean we don't even know like what particles are like fundamentally, or like what state they're actually in. Um, like until we observe it, when we observe it we get a single result, and we think of particles as like uh, we think of these particles as like a probability distribution of those results of that observable state.
So although there are many possibilities, there is only one end result,
Yeah,
and that one end result entails all the probabilities.
that end result is just one is just one observe it's just one observed item.
Oh,
So
it's just one over
yeah,
one
it's
out
like
of that many.
yeah, it's like one instance of a probability distribution.
Oh,
But like they can manipulate it so that the probability distribution is like tighter around the answer. But like for some algorithms it's very difficult to do that unless they just and what they do is they instead just run many trials. So
oh.
that can increase the confidence in the final answer.
But in quantum computing, the answer is the most confident. The end result is the most confident.
No, it's just one observation in the probability distribution. So we just know that it's within this interval.
How do
Like
you know the probability of that result?
through that's where like the theoretical physics comes in because they have this mathematical representation of it where they know, based on past observances and that these states are more likely with these conditions, and they've created this model of what the spin of a particle must be.
So it's based on past, not based on how the particle started in the current trial.
Yeah, it's based on its current like state and superposition. Again, we don't really know what the state is, but we have we have these models that I guess were both mostly deduced experimentally.
Okay.
That about how like particles behave and what the resultant probability distribution is like.
I see. So we treat the middle steps as a black box.
Basically, yeah.
I see.
Yeah. Yeah, that was actually an early critique of quantum computers that they were too much like a black box. But yeah, it is true. We don't know the middle steps, we just know the answer. And we know that we know based on like each circuit, like we can deduce from each circuit the confidence interval of the answer.
I see.
Like that can be like mathematically derived.
Oh.
But yeah, we like you can't get a certain answer from that. It's different knowing the probability of like the confidence and knowing like whether the answer is correct or not. Cool. Yeah, so this is Thoughtful Sundar building. This is the actual physical quantum computer
Oh, I see.
that Google has used.
That doesn't even look like a big computer.
Yeah, this is the cylinder's taken off, but it has to get like super cold. That's why it's like at the bottom of a cylinder.
Oh.
Yeah. So for the the starting question was like, how does this relate to finance? This is from the Wall Street movie.
What Wall Street movie?
The 1987 Wall Street movie.
Huh. No, I haven't
Yeah, it was
watched
just
that.
a movie about like what life on Wall Street was like.
I see.
It's a famous movie. So, yeah, why does Wall Street care about this? So, as I said, quantum mechanics are inherently stochastic. So we're not 100% certain of their outcome. They can't be really, they won't give us really determinate computation, which is why I think we might still use classical computation alongside them. But this is still is okay to have like only like to just have a confidence interval in many like simulation problems. And so obviously, like as we said, like in material science and quantum mechanics, quantum computing can help like simulate some of those like natural events. But there's also some financial simulations that stand to benefit. So like Wall Street uses stochastic processes to like predict the performance of stocks or to like establish the value of options, like to see what their likelihood is of going up or down and what the payoff would be. Like they use like these different algorithms to establish a probability distribution. Yeah, so this is sort of like high level for, it's not something I expect like common investors to employ, but like some of these, there are like algorithms like the Monte Carlo simulation that are used, I think, by like some day traders, and also like they probably use it in I think the Economist article suggested that they use it to like establish the asset price
I see.
to like determine what the asset price should be.
So they somehow found out the most probable result.
They find out a probability distribution
I see.
for how the stock should perform, and that's how they evaluate the asset. Yeah, so yeah, I guess they have like different parameters they take into account and do some like pretty advanced statistical analysis. Yeah, so this is one area where quantum computing could yield a pretty large benefit. So yeah, so this is I guess this is like a day trader or something.
Oh my god, that's a
But
day trader.
maybe I just got it from Google Images. It's like that's someone's monitors at Wall Street. But yeah, I'm guessing they have like these statistical methods kind of run automatically, and like this is also how they determine what the asset price would be. So like they'd have like a Monte Carlo simulation, which is basically, you could also call it like a random walk. So basically there are different steps you could take, like different, like at any moment of time there's like different ways that the stock could go, like different steps that it may take. It like performs those randomly, like in the near future, and does like many like numerous trials iteratively. So computers can do this very fast, and then like based on like the final results, like at some deadline, they can establish like probability distributions, like like a little bit into the future, so they can determine like how likely it is to go up or down.
This is like the AlphaGo, how they determine what the next move is.
Yeah, it's sort of like, it's like a stochastic process, just
Yeah.
like that. Yeah, and there's so finance is sort of like that. Like there's like a lot of different moves that could be taken, a lot of different factors to consider.
So do you need, in finance, do you need to take the politics, economy, all the external factors into consideration, or do you only take into the history into consideration?
I don't think they parameterize those, but they might. I think they might include like big financial metrics like the monetary supply. Yeah, I'm not really sure like what the actual code is. I just know that they actually run this like they do like run this Monte Carlo to just this, like basically they try to simulate all the different outcomes that they could foresee from the stock.
I once heard an experiment for which has a monkey throwing darts to decide which stock to buy, and then over like 10 years or something, the monkey performs better than like a fund manager.
I believe it because like fundamentally the prices are very stochastic.
But like if they have such a advanced tool like quantum computing, how could a monkey? That's basically just random problem.
Oh yeah, I think so. Whoever said that was probably speaking somewhat metaphorically, but like they do use a lot of just like random processes to decide what to invest in. And I think this isn't just used by the investors. This is also used by, I guess, like the stock exchange or whoever decides like the actual asset prices.
The stock price is only determined by the demand for the stock and the supply for the stock, right?
Oh, but
you can't set the price.
Maybe it's like the price of options. Yeah, I think that's what the article mentioned. Yeah,
that makes sense.
So those asset prices need some sort of like, you need some like forecasting to determine how valuable they should be.
I see.
So like, I guess like there's sort of like a competition between who's like selling the options and like the investors, and like how well they can forecast. So that's why like they will probably be some of the early people to employ quantum computing, because it's like a slight improvement over this. As I said, it's like fundamentally stochastic, and it's also like something different than classical computers is it's like true randomness. So like the random generators in classical computers are still like fundamentally determinate, and they, like if you know the seed, then you could reproduce those numbers. like quantum computers can be truly random because they're like the process itself is physically random.
Yeah.
So like, yeah, so it could provide a better model, and it could be, yeah, also much more efficient because like all these different outcomes could be held in superposition.
I see.
So yeah, this is some place where, yeah, it could, yeah, like I think like different firms will start implementing this early to stay ahead of the competition. And yeah, also like some scholars that I read, and also I think in the Economist article, they draw some parallels between quantum mechanics and economic effects, like the way that you don't really know the state of the particle until you observe it and it changes it. Like it's the same with asset prices where you don't know.
Oh.
You just have the flow of capital, and then you don't really know what it's worth until you actually sell it and put it on the market.
Well, I mean, for a stock, I know how much I can sell.
Yeah, but like I think there's like this analysis performed before it's given to you. How do you said it was like supply and demand, but where does that metric come from? Like what actual metric is it?
It is like how many people are willing to pay for a. It's like supply and
Yeah.
demand. Yeah.
So how do you know what the demand is? How do you know what the supply is?
I think the New York Exchange knows.
Oh, I guess the supply, you know. Yeah, but like I think they actually use some of these methods to like it's tough to evaluate like what the actual value is. Like it's not really known 100%. You just know the patterns of buying and selling. But like at any instantaneous moment, like you only know its history, and you like the value is sort of an extrapolation.
Interesting.
So that like that was what like some scholars in the article are saying, and that what the article was pointing out was that quantum computing was sort of destined for this because like markets almost behave in a quantum fashion where there's like any price is not really like some determinate object. It's like a state of like a suspension of possibilities.
I see.
So yeah, I think that's what they were saying. Yeah. So here's some more citations about basically how Monte Carlo and Markov chains could be sped up. Yeah, this shows that like Bayesian analysis could be much quicker. So yeah, basically statistics is going to be very efficient on quantum computers. And yeah, that's about it. Merry Christmas.
Merry Christmas. Let's thank John for such a thoughtful presentation.
Oh, happy to. It was fun. Well, thank you everyone for listening.
Thank you.